Once we have the network set up and we've got discovery in progress, it's pretty clear that we have a ton of messages that are flying around all over the network. These are REST messages, and typically they are going to be uh, reasonably small, I would think. Probably less than 500 bytes. You know, um, but there are a lot of them. Uh, the way discovery works is we ask uh, all of our peers who they are and who they know and what their default route is, and that's the same question over and over again, and the same answer over and over again. And in a traditional system each that uses REST, each one of those is a separate call, and the call has to get through to the other side. It has to be handled by the other side, and the reply has to be returned. At which point, you tear down the connection you just created and do another one for the next query. And that seemed to me to be, you know, hugely inefficient, incredibly inefficient. So I thought about it, and we did a few different things. First of all, we understood that all the data we were sending across, all this structured data, was in fact structured data, and that we could take a look at it and extract those portions of the system that were dynamic, store those portions that are static, and then when we get a request or a reply, when we get a string, we simply compare what we're getting against what was stored. And as long as we know the codex of the language that we're trying to parse, we can identify the elements that are dynamic and say this is the only thing that changed, and that's what we put on the wire. So that looks uh, in real life. If we take a look at a uh, we take a look at one of the messages that we have, let's say frognet echo is a simple message. So we say curl to http:// 10 250.250.1 / frognet echo. What we get back is a thing that says Seattle 5, 10, 250, 251, and then the rest of this stuff. That doesn't ever change. That's set once at the time we built the system, and we don't ever change it. Uh, the two on the right might change if we move around, but they change very infrequently, right? So why in the world would I send around a JSON bag that has all that text in it, or even worse, this one, get host. Sorry, get host.php. That returns a much larger string that is actually a formal JSON array. And you can tell it's a formal JSON array because it's got that little square brace, right? And you can grab this and take it to a JSON parser. Here we go. So we're going to go from instead of the epoch converter, we're going to use a JSON beautifier, JSON, sorry, JSON formatter. Oh, that's cool. Huh. The CloudShare handshake failed for the JSON formatter. That's never, okay. JSON checker, validation and formatter. Throw the JSON in here, and that's what it looks like, right? So we get it back. It's got the IP address, but this is well-structured JSON, right? And in this, none of this is going to change, right? The actual contents of this message may change somewhat, but they won't change within a run. And when they do change, they will change once, and then everything else that they get it until the next run is going to be the same. So there's no reason to send that over the wire. So we've got two issues that we're looking at here. One is that we can take a picture of the incoming request or the returned reply and identify those components of the picture which are potentially dynamic and use those to create a map of the system, and we can then place or construct a message that says use this original message and replace elements 2, 7, and 9 with the three values that are coming immediately after this map. And we do that, and that saves us all the rest of those bytes going across the wire. So we save those bytes, and that's cool. But we're still sending that same message over and over and over again, and we are creating a socket and tearing down a socket every time we do that. So the first one obviously is taken care of by the FrogNet architecture itself. I'm sorry, the second one is taken care of by the FrogNet architecture itself, because the proxy and daemon establish a single socket pair that is permanent. So there is no establish and tear down of sockets. That's all a facade that we put on for the application. You never know what's going on underneath, right? Just like you don't know what's going on, what a compiler does to create the assembler you use, right? That's the same thing. Uh, but you do that, and the first thing that happened uh, was that it's getting all these messages. They're all the same. They're executing them every time. We don't have to do the build up and tear down anymore, but we're still sending them over and still executing them. And we don't need to do that. So what we do is the first part of what I just described, the part where we're building the bits to put on the wire, right? That is the BLDC1. That is the Bullfrog Long Distance Communications Protocol number one. And then the protocol that we use to put it on the wire and tell us whether or not it's same or diff is the FrogNet Wire Protocol, FNWP1. And between the two of them, what happens is the BLDC1 generates the bits that we want to put on the wire, and then the FNWP takes a look at those bits, compares it to what's in the semantic cache, and it sends over either same or diff. And if it's diff, it sends over the map with what the differences are between this one and the last one. And so the two of them together then on the other side are used to reconstruct the message. The message gets sent to the Apache server. The Apache server services it. We get a reply back. We do the same thing. We look at the data that's there and compare it to the data that was there using the template for where things go and all that kind of stuff. And we generate a message that says these are the replies. We send it back. These are the reply diffs. We send it back, and we reconstruct the reply and send it back on to the user. And that's very cool. So now we've got a thing that says instead of sending over all these bits, we're going to send over a thing that says make the request the same as it was last time. And on the way back, we says make the reply the same as it was last time. So that's request repeat and reply repeat. And you can actually see these running if you look at a journal control. So you do a journal control minus U. Our three components are FrogNet proxy, FrogNet. You got to do a separate minus U, FrogNet daemon, and minus U frognet tunnel daemon v3, and we're going to do a no pager, and I'm just going to look at like the last, well, we're just going to follow it, see it live. Oops, not G, minus F. So what we're seeing here is this is a request diff. So we sent a request to the other side with a diff in it. We sent it, we received it. Here's a request raw, response same, reply same, right? So request, repeat, 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 diff, repeat. So what we're sending over here over the wire is very small, right? And I can prove that by using BMON. If this is this the right machine? Use this one. Yeah. So we do BMON, detailed, and what we're looking at is ETH0. So this is the downlink, nothing. WLAN 0, this is my uplink, almost nothing, right? WLAN 1. Okay, since I have WLAN 1 on here, again, not much, nothing. And this is during live conversation, right? All this stuff is happening and nothing is happening on the system. So the amount of data that we send back and forth is negligible, and we've got an interesting way we can kind of prove that too. So let me see. We're on hostname Seattle 6 right now. So what I'm going to do is this thing called pipe workload. Come on. So pipe workload. Okay. It's pipe workload.py. That's it. And you got to do yeah. And so it's got some various options we can use with it. The first thing you do is say where you want to go. So we're going to go to New York 1. Hang on, I got to shut this down. Uh, New York 1, and we're going to do an echo, and we're going to do 300 of them. So pipe workload, the first thing it does is make this request. Now this request is a Frognet echo, which is the same echo that I showed you before. And it makes it first to the Apache server run directly on port 8080, and then it runs the same request through Frognet. And when we're on port 8080 here, which is the way that you're doing it now, port 8080, we get a throughput of 4.0 requests per second. If we do it through the Frognet system, we get 4.7 requests per second, but we only sent 1 kilobyte instead of 39 kilobytes, right? Then we do a ramp down here. And again, on the ramp wire, we only sent 3.7 kilobytes instead of 145 kilobytes. And then down here, we get on the burst, we do 300 simultaneous. And I haven't told you why this is successful yet, but we get 365.3. And the savings here is we sent 12.3 kilobytes instead of sending 478. Okay. So that alone should give you an idea of the savings that you can get with semantic compression. But as I alluded to earlier with this Frognet burst, we actually took it to the next level. What the burst does is looks at the data that is in transit, and we look at it in two places. We look at it both in the proxy where it's originating, and in the daemon where it's being serviced. So remember, if you make a curl request, you're making it from your proxy to the daemon on your target. So in this case, our proxy is on Seattle 6 and the target daemon is on New York 1. And we're sending the same data. So we look at it and we say, when we get a request in on the proxy, we launch a thread and we put the bytes on the wire and we go to the other side. And that thread, the first thread, waits until the thing gets an answer on the other side, just like regular REST does. But in the meantime, we are accepting other requests, right? Up to, in this case, 300 of them. And they're all going in separately, and each one of them is launching its own thread. And each one of them is putting its own data on the wire. And on the other side, we pick it up and we do the same thing. We see whether or not we launch a thread, and that thread goes out and goes to Apache and services the request and sends the reply back. So what we do is when we launch a thread, we take a look and see whether or not we have any other threads for this same message already in progress, right? Already in flight. And if we do, then we make this thread wait until that thread finishes. And then we give the same answer to both of them because the answer isn't going to change. We do the same thing on the other side. If we get a request from 5 different machines for the same piece of data, we only ask once. We only ask the Apache server on the target once, and we send the same answer back to everybody. So that kind of message coalescing is how I can get 300 simultaneous requests per second to give me 65.3 requests per second. So 300 simultaneous requests queued, and they got through at 300 at 65.3 requests per second. And I've seen that number go up to 130, 140. The thing that constrains it are things like topology and other things going on the network typically. So we're going from here to New York 1, which means that we're going through the internet tunnels. Getting 65 isn't actually all that bad, although I have seen it go back up. Another one we can run, another test that we can run is instead of saying echo, we're going to do chat. And what chat does is gives us a approximately 20% new message rate on this chat window. So we're not going to get the same kind of throughput that we did with the echo test. It's not going to be anywhere close, but it's still going to have pretty substantial byte savings. So there was the basic Apache test. We got 2.7 requests per second through. On our test, we got 4.6, so we basically doubled it. But what we did, if you look at it here, so it says of the 25 that we sent, 15 were differences and 10 were the same. And for those 25 requests, we spent 6.4 kilobytes instead of setting 414 kilobytes. Same thing on the ramp when we brought it up. The interesting thing on the ramp is right here around 10, there seems to be a sweet spot. I often see this where it peaks around 10 and then drops back down again. So that's something that we want to look into and see. But then it comes down here to the burst where it's doing 300 simultaneous, and it gets through 20.4 requests per second. Of the 300 simultaneous requests, 222 of them were different, and 78 of them were the same. So it was a pretty nice mixed bag. And then we had 28.8 is all the kilobytes we sent instead of 4 megabytes, right? Almost 5 megabytes. And that brings me to the last test, which is kind of cool. There are other tests in here. If you just do a run it by itself, it will it'll show you what the options are. But the megabyte test is sending a 1 megabyte, 500 KB JSON with 6 dynamic fields back and forth. And I think it's actually 1 megabyte JSON. I think that's a misnomer. But at any rate, it's sending a big thing back and forth. And you can see that here in the BMON, it's actually doing that, right? We're actually getting that kind of indication that there is throughput going back and forth. And what we got is in the Apache mode, we got 0.9 requests per second. So what you're looking at here was the Apache mode. And if we go back up here to ETH0, now WLAN 0, yeah, WLAN 0, okay, and WLAN 1. So this is the one that's doing all the work right now. And what we did is the second one that we sent through on 1 megabyte uh, was 25 diffs, right? So we had 25, we sent through 25 different packets every time. And instead of sending 31 megabytes, we sent 92 kilobytes. Same thing on the ramp. And you'll notice here, this is interesting. The ramp went up the right way and it continued going up. So there was no peak on this ramp. And right now it's doing the 300 simultaneous requests with the 1 megabyte payload. So you can see up here on BMON, compared to what we saw when it was doing the requests directly to Apache, which is these things were very close together and very high. These things are much more correctly behaved. And what we got when we did it, here we go. So 279 of the 1 megabyte transfers succeeded. 21 of them failed. Those are most likely timeouts because I have a timeout on the query. So it can tie a failure is a timeout failure is not necessarily a failure. The answers probably came back later. But I got 4.4 requests per second through. But more importantly, I only sent 38 kilobytes instead of 347 megabytes, right? That's a huge difference. That's a huge savings on the wire. And it's the thing that lets me go from 0.9 to 4.4 requests per second, even though I'm sending a 1 megabyte payload, right? So it is awesome. And yeah, I know you're going to have to go verify those numbers. You're not going to believe me because I had to do it myself. I had to, when I saw the kind of compression, when I saw the kind of throughput I was getting here with this megabyte package, I had to go in and I actually did look at it very carefully and made sure that what I was printing out here was in fact the truth. So yes, semantic compression, same diff, the FogNet wire protocol, not creating sockets when we don't need to, all that kind of stuff really adds up. And what it can do is what we're looking at here is the ability now to send significant amounts of data, or at least significant structured data through very slow links, and they will work, right? So that's the whole promise and the whole premise behind semantic compression. It's not really compression. I know it's not compression, but I couldn't think of a better name for it. Semantic payload substitution didn't quite have the right ring to it. So we just call it semantic compression. And really, it's just the BLDC and the FNWP. So that's how we deal with semantic memory. The next thing we want to do is look at what goes into that memory, right? How does that work? So stay tuned and have fun. Well, this I hope you're finding this interesting. All right, take care.